So hi everyone, today we are going to design for the connection member. So in the previous video we just go through some detailed information about idea statica and how to use the ribbon tab. But today we are going to design beam to beam connection member. So let us start. So if you open the idea statica, then you can see these things popping in your screen. Then go to connection. That since we are making everything from the scratch, so just go to this one and then name anything you want, description, and then still grade. You can choose anything from here, like if it is yes 235, 275, 355, 450, and then bolt assembly. Now I am choosing M28.8 concrete grade and design code. You can design for your own country, but now I am choosing, I am in Europe, so I am going to design for the Euro code and then create a project. So in this one, at first we have to go to the member, and then from here we can select a lot of various things. So I'm going to make a I to I beam connection. So I, and then from here, from in geometry, you can change HEA, HEB, IP, HEM under the favorite. But if you go to all, then you can choose the several sections from here. So for now, we are going to just design HEA and HEB. So, and one thing just remain in your mind is like HEB section is always stronger, or the dimension is a bit bigger as compared to HEA sections. So if you open like HEA 100, then see it's like 96. But if you see HEB 100, then you can see it is 100 and the thickness of wave is also high. So you can choose it accordingly. For now I am choosing HEA 240. Okay. Okay. So and if you choose the perspective view, we can see it like this. So our cross section is HEA 240, and then geometrical type it should be continuous. The first member should be continuous, and then it is defined by rotation. So beta direction, it is just shows the direction, like if it is 90, the orientation is gonna change. Otherwise, it is the same thing. So it's nothing. And then we are giving, we can assign the force of everything like from here. So again, I am going to add another member M2. So, but the second member is gonna be HEA 200. Okay, you can see HEA 200, it has 190. If it is HEB, then it would be 200 by 200. So now we can see that these two members are aligned in the same orientation. So what we can do is just change this geometrical type into indent, and then beta direction 90 degree. Now if we do it like this, then we can see our member like this. So what we can do is, sometime if you want to connect this member to the wave of this one, then you can design it accordingly. But sometime if you just want the top of this section to align with the top of this one, then we can change it. So how can we do it? There are two ways. So how can we do it? There are two ways. So once if you go to Excel sheet, suppose we choose our member HEA 240. So HEA 240, then the total height from this to this section is 230. If we go to member, then HEA it's 240. Okay, then we can see from here to here it is 230. So centroid is 115. So I am not gonna take any member right now. So the centroid of member M1 is 230 and the centroid of member M2 is, because from here to here it is 190, so 190 divided by 2. So 230 is 115, 230 divided by 2 is 115 and 190 divided by 2 is 95. So if we took the difference between this and this, we will get 20. So what we can do is just put 20. It will go up like this. Or if you don't know the calculation, or if you are confused about the calculation, what we can do is just go to member plate, and from here just choose the related plate is M1 top flange, and then we can see it like this. If you want to align on top, then it is going to be on top, but here it is going to be on M2 wave 1, M2 top flange, because we want to like this, so we just want to connect M1 top flange to M2 top flange, so you can do it like this. So there are two process, whichever you want to follow, you can follow it, and you can see the modal type. So if you just want to give force on, so it depends on which force you want to give, so you can choose whatever you want. And forces in, I want to give the forces in bolt, so the force from this M2 member is going to be transferred into the bolt, and then after that it is going to get transferred to the member M1. So it is also done, but now we can see these things overlapping. So if you try to run this model, then there will be so many errors. So what we need to do is we need to do some operations. So do operations and provide knots. So if you click that one, you can see the knots on the member M1, but we want knots on member M2. So member M2 top flange, and then because it is flange and this is wave and this is flange, so member M2 flange, shape is knots. So from here, as you can see, this is showing 40. So what we can do is, we know the dimension from of this flange, so it is 200. We can just choose 200. Then this 80 is like the distance from the centroid to this part. So what we can do is, since this is 240, so the 240 half is like 120. So if we just choose like 120, then it will just get like this. But if you want a more workable shape, then you need to choose like 140. Okay, now this looks fine. And then again, we need to create a knots in the web. This is for flange, so we need to create knots in web. So just go to operation, knots. It is M2 web 1, and then shape knots. So if we do it like this, we can see the knots has been created on this part, but we want the knots on this part. So what we can do is location, rear. Rear means on the back side. Now you can change the knots. Like 80 is like from center of here to this one. So look, just be careful, okay? So if I take here 130, 140, because this one was 140, so let us take 140, and then depth maybe 20. 20 is a bit less, so 25. and then I will create a rounding radius of 20. So this one is also done. I hope you are understanding up to here. Now after that we need to connect this memory M2 with M1. So what we need is we need to go to operation and we need a int plate, beam to beam or beam to column connection. So int plate of 8.8 bolt assembly M20. Okay. So if we do this, then we can see a lot of warning messages. But just leave it, or if you want to go through it, then we can try to resolve this warning message. So the first warning message is memory M2 passes through memory M1. It means memory M2 passes through memory M1. So if we go to transparent view, we can see that this memory is passing through this int plate and also through the memory M1. So we need to pull the memory M1 or we need to offset the memory M1 on this direction. So we need to go to memory M2. So memory M2, because memory M2 passes through memory M1. So offset EX. Now what we can do is, so sorry, what we can do is like the thickness of this thing is 8 millimeter. The wave thickness of memory M1 is 8 millimeter and the plate thickness is 12. So thickness is 8, so 8 divided by 2 is 4, so 12 plus 4, 14. So if we click here 14, then it is gone. You can understand the calculations here because from here to here it is 8 millimeter. So from the centroid it is 4 plus plate thickness. So 12 plus 4, 16. So our plate thickness is 12. So if we go to solid, so this is 12 plus 4. 16, it should be 16. Yeah. Now warning is gone. So, and it says like EP1 in plate crashes through memory M1. It means this. Because it is popping like this. So guys, so what we can do is we can go to EP1 and then let us work. So top we can see 8. So if we can do this to 15, sorry, minus 20. So we can see the warning has gone like this. You can choose whatever the plate size you want. So this is for the practice purpose. So top minus 20. So bottom also we can see this part is coming. So let us took bottom as minus 10 maybe. Okay. Then it looks like this. Then left means left. So you can see if you put 10, then 10 is gonna get increased. Right, also 10. So our whole plate length is 220 by 160. 220 by 160. So after that, let us go to the bolt. So if you want to choose M16 8.8, these are the grades you can choose from. So now I am choosing M16 8.8. Okay. So now we can see, and let me delete all these things for now. So it will be easy to understand. So top layer means the number of bolt on top layer. So if I do minus 50, then we can see that the difference between the top to this one is top to the centroid of the first bolt should be minus 50. So left layer maybe I will take minus 60. Minus 60 is a bit more, so let us take minus 30. So we can see minus 30 from here to here. And again, right layer also I am going to choose minus 30. So now what I can do is just go to top layer and then just do space, right space, and then just maintain the spacing between your bolts. Suppose if I want the next bolt at minus 60, then we can see next bolt is appear, and again click here, space, minus 50, minus 50, minus 45, and then minus 60, minus 55. Now it looks a bit symmetrical. So, but you can choose this according to your design. For now, this is just a practice purpose. So I took it like this, and then after that we are choosing the weld on the both side of. For the flanges it is 4, and for the web if you want, then you can also choose your web, or you can make it to 0. It doesn't matter, it depends upon the design that you are going to do. So after this our model is complete, so just click calculate. Then we can see there are no loads on member, so we need to add load. So we are adding load on yum to end, 50 kilonewton. If there is moments, then you can add it accordingly. So just to calculate. Now this is one of the greatest problems that I have been encountering all the time. So singularity means so it generally occurs if there is a gap between members and plates. So if there is a gap between this member M2 and plate, then there will be singularity error. So just go to transparent. And then just go to member M2 and then play with this offset. Maybe if we choose 14, 15, and then try to. Then we see EPS passing through. Then we can see that there is our error EP1 weld passes through M2. Weld passes through M2. So if you go to M2, 15, 12. There is like a weld class warning, EP1 weld passes through M2. So in plate 1 weld passes through M2, like from here I think the weld is passing through M2. So just try to keep on playing with this one. Then there is singularity error. If I do 15, 15.5 maybe. So it is, there is something like this. This model is correct. As you can see, the analysis is passed. Plate is also fine. Bolt is also like just 17.6% utilized. Welding is also okay. Buckling is not calculated. If you want to calculate the buckling, then you need to go to code setup, I think. No, but it's fine. But I don't know why this error is popping. But maybe if you play with this thing a bit, then this one will also go, and this is not a bigger issue. So since our modal is passed, then just go to check. From here you can check like stress in contact. Like we can see where there is bolt, there is a lot of contact force like this, and you can check the bolt force 3.224, 2.4, or you can see the deformed shape, equivalent stress, everything. So after you generalize your result, then just go to report. Then here you can just click everything you want, and then generate. Then you can see well generated report that will give you descriptive information about each and everything. So guys, I hope you have learned something from this video. If you have anything, if you don't understand anything, then just please leave a comment and I will try to solve that one. So you can also practice and have fun with IDA Statica and just wait for the part 2 tutorial. Till then, bye, take care, have a good time.